Yo, welcome to Physics with Vinay.
So in this lecture, we're going to start off with circular motion. So particle traveling in a circular motion, the velocity v is tangential, let's say the radius is r. So the acceleration vector of the particle traveling in a circular motion has two components. One, what we call as the tangential component, and one towards the center, what I'm referring to as the normal component, also known as the centripetal acceleration. The tangential is nothing but dv by dt, and the normal component is equal to v squared by r. So these are the two components of the acceleration of a particle in circular motion. The resultant acceleration will be in this direction. If the particle is speeding up, then the tangential component of acceleration will be parallel to velocity. If the particle is speeding down or decelerating, then the tangential component of acceleration will be opposite to velocity. We also define some angular variables here. We define the angular displacement as this angle, the angle traveled by the particle. Angular velocity is simply the rate of change of theta. So angular velocity is defined as a vector whose direction is given by the direction perpendicular to the plane of the circle. When you curl your right hand around the circle in the direction of motion, the direction of the thumb will give you the direction of angular velocity. So if the particle is traveling in the anti-clockwise sense, the velocity is in the anti-clockwise sense, the motion is in the anti-clockwise sense, and the angular velocity will be outwards. If the motion of the particle is in the clockwise sense, the angular velocity will be inwards. And you can express the velocity vector as omega cross r in terms of the angular velocity and the position vector. Position vector is basically the radius vector measured from the center of the circle. And finally, angular acceleration. So that is nothing but d omega vector by dt, the rate of change of angular velocity. So if I have angular velocity in this sense, that means the particle is traveling in the anti-clockwise sense, and suppose the particle is speeding up. So omega magnitude is increasing. So angular acceleration will be parallel to omega. If it's speeding down, angular acceleration will be anti-parallel to omega. One thing to realize is that the motion of the particle along the tangent, along the circumference, I can make an equivalence to this motion. Suppose the initial velocity is u, the tangential acceleration is 80. If I just open this circle up, so I have a particle traveling with velocity u and tangential acceleration 80. So you can use all the equations of motion that you learned in kinematics. So basically I can write the tangential acceleration is dv by dt is also equal to v dv by ds. ds was a displacement along the straight line. So here will be displacement along the circumference. And of course v is ds by dt. So for example, for constant tangential acceleration, and just write v equal to u plus at, where a becomes the tangential acceleration, I can write s is equal to ut plus half at squared. Now here you have to realize what is s. S is the distance or the length of the path traveled along the arc, along the circumference. This is s. Now if suppose the initial velocities, let's say in the anti-clockwise sense, but the tangential acceleration is a constant value in the clockwise sense. So at some point, the velocity of the particle will become 0. You can use v equal to u plus at, set v equal to 0, and get the time at which the particle comes to rest. After that, the particle will start traveling in the clockwise sense. So let's say after some time t, the particle is here. So my point of this example is to show you what does S mean here. So S will be the displacement. If you just open it up and imagine this as a straight line motion, or the motion of that particle would have come to rest at some point and then traveled back. So at some other instant, the particle is here at this red point, corresponding to this. So if you use S equal to ut plus half at square, what length are you actually measuring? You're measuring this green length, that is your final displacement. So in this situation, you're measuring this arc length from the initial position to the final position. So that will be your S that comes from this equation. It's not the total distance traveled, it's definitely not the displacement, it's the arc length between the initial and the final position. Okay, now let's do a question. Two particles A and B are moving towards each other on a straight line with equal speeds 5 meters per second. At an instant that is assumed to be t equal to 0, distance between the particles is 100 meters. It is desired to move another particle C, always maintaining a distance 40 meters from particle A and 30 meters from particle B. So what's the modulus of acceleration, the magnitude of acceleration of the particle C at t equal to 5? So you may be wondering what this question has to do with circular motion. Well, in the ground frame, there is no circular motion happening. However, whenever you have a question where a particle is at a fixed distance from another particle, that means in the frame of one particle, the other particle has to perform circular motion. So let's take a look at how we can solve this question without resorting to any sort of calculus. So at t equal to 0, they are at 100 meters, particles A and B. And they're traveling at 5 meters per second. So the velocity of approach is 10 meters per second. And at the instant of t equal to 5 seconds, the distance between them would be 50 meters, because the velocity of approach is 10 meters and the distance would have decreased by 10 into 5, 50 meters. Okay, now the particle C is at 40 meters from A and 30 meters from B. So you can see a nice right angle triangle forming here. So the question is asking, find the acceleration of the particle C at this particular instant. Alright, so if I go in the frame of A, C will be performing circular motion of radius 40 meters. So C will have, let's say, an acceleration this way. Let me call it AX, and acceleration this way. Let me call that AY. So for the circular motion of C about A, AY will be like the centripetal acceleration, AX will be like the tangential acceleration. So can I write AY would be equal to velocity of C with respect to A squared divided by the distance, the radius, which is 40. So now I need the speed of C with respect to A. Now that is also pretty straightforward, because in the frame of A, let's say C has a velocity this way, velocity of C with respect to A. Now B has a velocity of 10 meters per second with respect to A. And because the line BC has a constant length of 30 meters, therefore, let's say this angle is theta, can I write VCA should be equal to 10 cos theta? The components of C and B along the line joining BC should be the same. Only then the distance BC will be a constant. Now cos theta is very straightforward from this triangle, which is 3 by 5. So this will be 36 by 40, 9 by 10 meter per second squared. And now we have to just do the same procedure in the frame of B in order to calculate AX. So if you want, you can pause the video and try it out, try the rest of the problem by yourself, and then you can take a look at what I have done. Alright, now I'll go in the frame of B. So let me go to the next page. So in the frame of B, A is coming to the right with 10 meter per second. And let's say C has a velocity of VCB with respect to B. And this is, let's say, phi. This triangle was 40, 30, 50. So once again, can I say velocity of C with respect to B should be equal to 10 cos phi? Same logic. The fact that AC has a constant length, so the velocity components along AC should be equal. So this will become cos phi is 4 by 5. Alright, now in the frame of B, C has an acceleration, what we labeled as AX in this direction, and AY is something that we already calculated. So AX would be velocity of C with respect to B squared divided by the radius is 30 meters. So 8 squared by 30. So 32 by 15 meter per second squared. Alright, so the acceleration of C, see in the ground frame and frame of A and B are all inertial frames. So acceleration of C will simply be, we found out 9 by 10 as AY plus 32 by 15 the whole squared. And this will come out to be around 2.3 meter per second squared. So this is the acceleration of C in the ground frame. Now let's look at the concept of angular velocity when the particle is not performing circular motion. So in general, if I have a particle here whose position vector is r vector, and let's say this is the velocity vector of the particle. So let's say velocity vector is making an angle of alpha with the position vector. So I can break down my velocity vector into two components, v cos alpha and v sin alpha. So the angular velocity about the origin of the particle, about the origin, is nothing but d theta by dt, and that comes out to be the velocity component that is perpendicular to the position vector v sin alpha divided by the position vector magnitude. So v sin alpha divided by r. So this is what the angular velocity comes out to be. And what does v cos alpha do? V cos alpha changes the length of the position vector. So dr by dt. So this is a useful relation. Suppose you have two particles. Let's say v1 alpha, v2, and this angle is beta, and this is length is L. So I want to find the angular velocity of the line connecting these two particles. Let's say particle 1 and 2. So if I go in the frame of one of the particles, then it's like this situation where one of the particles plays the role of the origin O, which is fixed, and then you can define angular velocity as the perpendicular component of velocity divided by the length. So here in this case, if I just write velocity of 2 with respect to 1, and the perpendicular component perpendicular to the line connecting them divided by L. So what will be v21? The relative velocity would be, see, this has a component perpendicular to the length as v2 sin beta in the downward direction, and this has v1 sin alpha in the upward direction. So the relative velocity would be v2 sin beta plus v1 sin alpha, plus because they are in opposite directions divided by L. So this will be the angular velocity of the line connecting points 1 and 2. Let's take a look at a couple of questions. A particle P is moving on a circle under the action of only one force acting always towards fixed point O on the circumference, and find the ratio of d2 theta by dt squared and d theta by dt the whole squared. So in this circular motion, let's say the particle is here at some instant, and the force is directed from the particle to O. Let's say this angle is theta. So then obviously this is 2 theta. The angle subtended at the center is 2 theta. Now what is being asked? Can I say that angular velocity of the particle about the center would be d by dt of 2 theta. So 2 d theta by dt. So d theta by dt the whole square is basically omega squared by 4 from this. And what about d2 theta by dt squared? If I just differentiate this, I'll get the angular acceleration about C, about the center. I've just differentiated these two and I've got an alpha is equal to 2 d2 theta by dt squared. So d2 theta by dt squared that is being asked in the question is basically alpha by 2. So I basically need to figure out the alpha and omega squared. Okay, now can I say that the component of this force towards the center would be f cos theta, should be equal to m omega square into radius, and the component of the force tangential f sin theta. The tangential acceleration is nothing but alpha times the radius, angular acceleration into radius, so that will be m alpha r. So if I just divide, I'll get tan theta as alpha by omega squared, and what do I need? I need a ratio of alpha by 2 and omega square by 4. So alpha by 2 divided by omega square by 4 will be nothing but 2 tan theta, and that is your answer. So I hope you have understood how we related the rate of change of angle about some other point to the angular velocity of the particle about its center. So here we have a question in which it looks like a laws of motion problem. It looks like a difficult laws of motion problem, but in such question I'm going to show you how to convert this into an easy circular motion problem. So first let's just read the question. A bead of mass m which can slide on a straight horizontal frictionless rod is being pulled with the help of a light inextensible thread of length L. So this is the bead that can slide over the smooth rod and it's being pulled by the string in such a manner that the end P of the thread which is being pulled moves with a constant speed V0 always directed towards or along the thread. So this end P always has a velocity along this thread. Find an expression for the tensile force T in the thread at an instant when the thread makes an angle theta with the rod. Alright, in such questions where you have a particle and connected by an inextensible thread, always go in the frame of one end of the thread, because if I go in the frame of point P, the bead is going to be at a constant distance from point P. That means its motion is going to be circular motion. So what I'm going to do is I'm going to convert this problem which looks like a tough laws of motion problem into a simple circular motion problem by simply going in the frame of the end of the thread. Now because the question is asking tension force, what do I need? See, I'll have a tension force this way and the acceleration of the bead will be to the right. So can I just write T cos theta is ma. So if I can get the acceleration of the bead, I'll get my tension. So that is my aim now, to get the acceleration of the bead. So for that I'm going to go in the frame of point P. So in the frame of point P, this bead is going to perform circular motion. So let's say its velocity is v relative. Now how much will that velocity be? So end P has a velocity of v0. So this should be v0 here. See, I know that in the ground frame, the bead has a velocity v to the right and point P has a velocity v0. They'll both have the same velocity components along the string. That is the constraint equation. So the only velocity component that will remain in the frame of point P would be v sin theta, the component perpendicular to the string, and that will be v relative. Now I want to express it in terms of v0, so I can just use the constraint equation that v cos theta is v0. So v is v0 by cos theta, so this will become v0 tan theta. So v relative is v0 tan theta. Now, can I write the component of acceleration of bead along the string, the normal component in the frame of point P, will be nothing but v relative squared by L. So this is the main equation. In such problems, what we're going to do is we're going to write the component of acceleration along the string, because that will be the centripetal acceleration. In point P frame, bead is performing circular motion. So this will become my centripetal acceleration. Now, I would like to express An in terms of the acceleration of the bead in the ground frame. Now, the question says that the point P has a constant speed always directed along the thread. So therefore, the acceleration of point P along the string will be 0, because there is no change in the velocity component along the string. So any acceleration of point P will be perpendicular to the string. In general, I can write acceleration of bead with respect to P should be equal to acceleration of bead minus acceleration of point P, but I only need the normal component. So the normal component is 0 for the point P. There is no component of acceleration of point P along the string. So the normal component of bead with respect to P will simply be the normal component of bead in the ground frame, which is nothing but a cos theta, component of A along the string. Alright, so that's it. We are going to substitute an here and we're going to substitute v relative here. So what we get is a cos theta should be equal to v naught squared tan squared theta by L, and thus you get acceleration from this equation, and once you get acceleration we get tension. So just substitute acceleration from this equation here and you'll get your tension as v naught squared by L sec square theta tan square theta. So I hope you've understood how we converted this difficult looking laws of motion problem into a straightforward circular motion problem simply by going in the frame of one end of the string. Now let's look at banking of roads. So on a flat road, when a car is traveling this way, we have to realize that when a vehicle is traveling, it is static friction that acts. The wheels are rolling and it is static friction that acts on vehicles. There is no slipping between the tires and the road. If there were slipping, then that becomes dangerous and that becomes risky, especially when the road becomes slippery. Then the maximum friction reduces because the coefficient of friction reduces, and therefore the car can negotiate a turn at low speeds. They cannot go very fast because of the low friction, otherwise the cars will tend to slip. And therefore what is done is that the roads are constructed at an incline. So the road is constructed at theta, which is called the banking angle. The car is going inwards. The car has a velocity inwards. It is performing a horizontal circle. So the entire road is inclined at an angle theta. So let's say the radius of curvature is r, and we want to figure out the minimum and the maximum possible speeds at which the car can negotiate this turn without slipping. So that means the friction has to be between 0 and mu n, where mu is the coefficient of static friction. Alright, so for maximum speed, you can imagine that for maximum speed we need the maximum possible acceleration, and therefore in addition to the forces of normal force and gravity, we would like friction to help out the normal force and provide that extra acceleration. So the friction, we will assume it is acting downwards, and let's say set that to mu n for the maximum possible acceleration. So the acceleration will be in the horizontal direction, which will be the centripetal acceleration. The car is performing a horizontal circular motion, and therefore the vertical forces will result in a zero net force. So let's just write those equations. My FPD would be a normal force, an mg, and mu n in this manner. So in the vertical direction, can I write n cos theta should balance out mu n sin theta plus mg, and in the horizontal direction I can write to the left n sin theta plus mu n cos theta should be equal to mv squared by r. And just eliminate n by dividing the two equations. Just eliminate n and you will get v, which will be the maximum speed. You don't have to remember the expression. You can just solve this set of equations in the exam. And what about minimum speed? See, one thing is that if the coefficient of friction is large enough that mu mg cos theta is greater than mg sin theta, that means there will be no slipping in the downward direction. That friction is sufficient to balance out the component of gravity. That means the minimum speed, basically the car can remain at rest. So the minimum speed will be 0. On the other hand, if mu mg cos theta is lesser than mg sin theta, in that case, when the car is performing circular motion, for the minimum possible speed, that means minimum possible acceleration, we would like the horizontal component of friction to oppose the horizontal component of the normal force. So friction will be acting upwards. And just write the same equations like we did here. Just balance the forces in the vertical direction. This time you will have n cos theta plus mu n sin theta is mg. And in the horizontal direction to the left, I'll have n sin theta minus mu n cos theta is mv squared by r. And then once again, you can divide and get the minimum speed. Just make sure that you are working under this condition. As soon as in the question you see that mu is greater than tan theta, you can immediately say that the minimum speed has to be 0, no need to do any calculation. For any other speed between this minimum and maximum, the friction will lie somewhere between these two, between mu n downwards and mu n upwards. So there will be static friction lying between these two. Let's look at the concept of radius of curvature. So radius of curvature, if you have any trajectory, at any point, suppose the velocity is v, that portion of the trajectory, that infinitesimal portion of the trajectory can be considered to be part of an imaginary circle. What I mean by that is that a circular motion means that the acceleration should be in the form of v squared by r, the acceleration component perpendicular to velocity. So let's say that component of acceleration perpendicular velocity is a perpendicular. That should be equal to v squared by r, and this r then becomes the radius of that imaginary circle, which is also called the radius of curvature. So for example, I have a projectile motion and initial angle of projection is theta and velocity is u and acceleration due to gravity is g. So if I want to find the initial radius of curvature, I'll need to find the component of acceleration perpendicular to velocity. So that will be g cos theta, and therefore the radius of curvature would be u squared divided by g cos theta. So that's how you figure out the radius of curvature. A sharper curve will have a smaller radius of curvature. So if they ask you to compare the radius of curvature at A and B, at A it will be, the magnitude will be smaller than the radius of curvature at B. Now, if you given the equation of the trajectory y as a function of x, then the radius of curvature at any point is given as 1 plus dy by dx the whole square raised to 3 by 2 divided by. So this is the expression for the radius of curvature at any point of the trajectory given y as a function of x. Now let's take a look at a question on radius of curvature. So suppose I have a particle thrown with velocity u and angle of projection is theta. This is a projectile motion. Now an insect flies along the same trajectory. With a constant speed u. So along this blue trajectory the insect flies, but with a constant speed u. The question is asking us find the force of air on the insect at the highest position. So on this initial particle that was thrown, let's say it's a stone. So on that stone, there was no effect of air resistance. We are assuming the stone is heavy enough to avoid air resistance, but of course an insect is flying due to the force of air. So I want to find the force of air on the insect at the highest point, and let's say insect has a mass m. Alright, so if you want, you can pause the video and give it a try, and then you can take a look at my solution. Okay, so the key point here is to realize that the trajectory is the same for the stone as well as the insect, and therefore the radius of curvature at every point of the trajectory is going to be the same. Radius of curvature depends only on the geometry of the trajectory. It doesn't depend on the motion of the particle or the insect as long as the trajectory is the same. So at the highest point, in the projectile motion, what is the radius of curvature? I know the acceleration is g, I know the velocity is u cos theta, and the acceleration is entirely perpendicular to the velocity, so the radius of curvature will simply be v squared by r, v squared by acceleration, so u square cos square theta by g. Now for the insect has a velocity u, it has the same radius of curvature, and it won't have any tangential acceleration because the velocity of the insect has a constant magnitude, constant speed. And therefore this acceleration, can I write it as u square by the radius of curvature, and substituting this radius of curvature, I'll get it as g sec square theta. Okay, so now the FBD of the insect has an mg and a force of air, so can I write mg plus f should be equal to m into acceleration, which is g sec square theta in the downward direction, and thus I get my force as mg tan square theta. So this is the force on the insect by the air at the highest position. Now let's come to the rotating frame of reference. So let's say I have a coordinate axis x, y, z, which is rotating about some axis. So let's say the rotating frame has an angular velocity omega vector. So in the rotating frame there are what we call three pseudo forces: centrifugal force, Coriolis force, and Euler force. Coriolis and Euler are not in a syllabus, so I won't discuss those forces. I will, however, talk about the centrifugal force. So centrifugal force is given by m omega square r, where omega is the frame, angular velocity of the frame, and r is the distance from the axis of rotation, and the direction is radially outwards. So it's radially outwards from the axis of rotation. So this is the centrifugal force, it's the pseudo force in the frame of the rotating frame. So for example, if I have a disc, I'm looking at the top view. So this disc is in the horizontal plane, and let's say I have two blocks. So let's say this is L, this is also L. The string length is 2L. So two blocks are connected by a string. So this is a top view. Let's say the left block has mass m, the right block has mass 2m, and the disc is rotating with constant angular velocity omega, and the coefficient of friction of the disc is mu. The question can ask, find the maximum possible omega such that the blocks don't slip. So if I draw the FBD of the blocks in the disc frame, once again I'm looking at the top view, so I'll have 2m omega square, the distance from the center is L. So this is the centrifugal force radially away from the axis of rotation, it will be m omega square L. Then there will be a friction force mu into 2mg and mu into mg. So here in the diagram I am considering the system to be just on the verge of slipping. So the resultant of 2m omega square L and m omega square L must try to move the set of blocks to the right. So I can just write 2m omega square L minus m omega square L should just be able to overcome the external friction, which is 3 mu mg. And therefore you will get the maximum omega as 3 mu g by L, square root of that. So this is the maximum omega such that the blocks don't slip on the disk. So I hope you've understood this example and how we use the concept of centrifugal force to do this question. Now let's look at the concept of work. So work is defined as integral f dot ds, where ds is the displacement of the point of application of force. If the force is a constant meaning magnitude as well as direction, I can take the force outside of the integral and this will come out to be f dot s, whereas the net displacement. So for example, gravity, if I have a particle going from A to B by any path, but the height difference is h, the work done will be the dot product of gravity as well as the straight displacement, and therefore I'll simply have it as mgh. Now what will appear is the component of the displacement along the vertical, because the force is along the vertical. So if a particle is being descended or taken down by height h, the work done by gravity would be mgh. And similarly, if the particle is being taken upwards, the work done by gravity would be minus mgh. Now net work done by normal and tension when the strings are taut or the bodies are in contact is 0. So this is the foundation of the virtual work method, and the reason is that for normal force, suppose I have this sort of an example, both the block as well as the wedge will have the same component of displacement along their common normal, otherwise they lose contact. Because they have the same displacements, the normal force on block 1 is acting in the upward direction, whereas the normal force on block 2 or the wedge 2 is acting in the downward direction, and therefore the work done on block 1 and block 2 will cancel out. The work done by the normal forces will be equal in magnitude because the displacements are same, but the directions are opposite, and therefore the net work done will be 0. And very similar reasoning, the work done by tension is also 0. Now, if we talk about conservative forces are forces whose work is independent of the path taken. And the most common examples are gravity and spring. So for such forces, we can define the concept of potential energy. And potential energy is basically defined as a function of the position in space. So that means that it is independent of the path taken during a process. So if a particle is taken from point A to point B, I can simply write the change in potential energy is the negative of the work done by the force, whose potential energy we are writing. So when we write change, that is always final minus initial. So this is the definition of potential energy. And using this definition, we get the potential energy of gravity as mgh. So here we have to take a reference line. Suppose this horizontal reference line is the level at which the potential energy is assumed to be 0, and you can choose this wherever you like. So at a height h above, the potential energy would be plus mgh, and at depth h below the reference line, the potential energy would be minus mgh. This is for a gravity. And for springs, the potential energy is given by half kx squared, where x is the compression or extension. Here also we've actually made a choice that the potential energy is 0 at the natural length, and that is once again a choice, and you can choose the potential energy to be 0 at some other point, but this is the mathematically most convenient and the standard convention. Here k is of course the spring constant. Now let's look at the most important equation or theorem in this chapter, the work energy theorem. So work energy theorem states that the net work done by all the forces, this includes external as well as internal, conservative, non-conservative, everything, is equal to the change in kinetic energy of the system. That means the sum of the changes in kinetic energy of each constituent of the system. Now, if the work done by the non-conservative forces is 0, then that means the mechanical energy, the total mechanical energy will be conserved. That is nothing but the conservation of energy, mechanical energy. The total mechanical energy is the kinetic energy of the system plus the potential energy. So this is the basis of pretty much every problem that you will have to solve in this chapter. You will have to use either work energy theorem or energy conservation. So let's take a look at a couple of questions. So let's say I have two blocks. M1 and M2. Spring constant is K, friction coefficient is mu1 and mu2. The question is asking us find the minimum value of this force to move block M1. The first thing is that in order to move block M1, the spring force has to overcome the static friction, the maximum value. So Kx should just be equal to mu1 M1g. Now when can the spring apply the maximum possible force on M1? That is the situation we want here. The maximum possible force of the spring is when the extension in it is maximum, and at maximum extension, remember M1 is stationary, only M2 is moving. So at maximum extension, M2 will have 0 velocity. Don't make the mistake of thinking that at maximum extension M2 will have 0 acceleration. That's a common mistake. That is not the case. At 0 acceleration or at the equilibrium position of M2, it can still have some velocity, and thus the spring can still further extend. So at maximum extension, it is the velocity of M2 that will be 0. If it had some velocity, the spring will further extend. So at maximum extension, M2 will have 0 velocity, and therefore what I can do is I can write work energy theorem. So I'll write work done by the external force. So let's say the spring extends by x, that means the block M2 is traveling by x. So F times x. The work done by the spring, can I write it as the negative of the change in potential energy? So negative of final potential energy is half kx squared and initial is 0. What about the work done by friction? The friction force is acting to the left of mu2 m2g. So minus mu2 m2g times x. And the initial system was at rest. Finally also M2 will be at rest, and therefore the change in kinetic energy is 0. So I've just written the work done by force, spring and friction is equal to change in kinetic energy, which is 0. And thus we get the value of Kx from here. I will get Kx as 2F minus mu2 m2g. And this value should just be equal to mu1 m1g. There should be a 2 here. Here, I missed that out earlier. Alright, so I'm just going to substitute Kx as mu1 m1g, and therefore I will get F as mu2 m2g plus mu1 m1g by 2. So this is the minimum force in order to move block 1. Let's take a look at another question. A small bucket of mass m rests at the bottom of a pit that has a depth h. A motor with an elastic cord is used to lift the bucket out of the pit. One end of the cord is attached to the bucket, the other end is attached to the shaft of the motor. So let me just draw the diagram. So there is a pit where there is a bucket of mass m and it's connected to a motor. And the cord is elastic. There is a mark on the cord at the height 0.8h from the bottom of the pit. So let's say there is a mark here. This is 0.8h. The cord is vertical and relaxed but taut. So what this sentence means is it is at its taut length. So that means if you just slightly pull it, it will go under extension and generate tension in the cord. And relaxed means that it is at its natural length, but a slight pull will extend it and produce tension. So the motor begins to rotate slowly. It is noticed that the bucket loses contact with the ground just as the mark on the cord reaches the shaft. So when this mark reaches the shaft means it reaches this highest point, the block loses contact. Assume uniform extension over the whole length of the elastic cord, and the question is asking us to find the force constant of the cord and the work done by the motor. So if you want, you can pause the video and give it a try, and this is a very nice question. So give it a try and then you can take a look at my solution. Alright, so first let's figure out the extension in the elastic cord. Because 0.8h extends by 0.2h, the total length here is h, and this red mark is coming to the top of the shaft. So therefore the 0.8h portion of the cord has extended by 0.2h, and therefore it's extending by 1/4 of its natural length. Now here the question says that assume uniform extension over the whole length of the elastic cord. So therefore h will extend by 1/4 of it, so h by 4. So the entire cord is extending by 1/4 of its natural length, and therefore the force is going to be kh by 4. And of course you have mg, so kh by 4 is equal to mg, and therefore spring constant is 4 mg by h. So this is your answer. This is the force constant of the elastic cord. Now calculate the work done by the motor till that moment. Now I can just say that the work done by the motor plus work done by the spring should be change in kinetic energy should be 0. Till that point the block has not actually lifted off. So work done by the motor is simply negative of the work done by the spring, which is nothing but the change in energy of the spring. That was the definition of potential energy. Change in potential energy is negative of the work done. And initially the spring was at natural length, so 0 potential energy, and finally it is half k into extension is h by 4. So just substitute k that we found out here. So this will come out to be mgh by 8. So this is the work done by the motor by the time the cord gets extended by h by 4. So I have a block, let's say mass m, spring constant is k, let's say the coefficient of friction is 1 by 8, and the spring is compressed by mg by k and released. So the block will oscillate, but because of friction it will eventually come to rest. So the question is asking us to find the total distance travelled. Till it comes to rest. Till it comes to permanent rest. Alright, so this is a tricky question. If you want, you can pause the video and try it out and then take a look at my solution. Alright, so first thing, let's say that from the natural length, let's say the spring is compressed by x naught, and when it comes to rest, again on the right hand side of the natural length, let's say that extension of the spring is x1. Okay, so let's find a relation between x0 and x1. So let me write work energy theorem. So work done by friction. So work done by friction would be as the block travels to the right a distance of x0 plus x1. The work done by friction would be minus mu mg into x0 plus x1. What will be the work done by the spring? That will be the negative of change in potential energy. So final potential energy is half k x1 squared minus initial potential energy. Should be 0. The block has started from rest and ended up at rest. So the change in kinetic energy is 0. I can write mu mg times x0 plus x1 should be equal to k by 2 x0 minus x1 times x0 plus x1. and therefore I will get x0 minus x1 as 2 mu mg by k. So you should be able to see that every time the block goes to the other side of the natural length, the compression or extension is going to reduce by a constant amount of 2 mu mg by k, and in our case mu is 1 by 8, so this will be mg by 4k. So initially the compression was mg by k as given in the question. So let's say this is the natural length. So initially the block was here at a distance of mg by k. Then on the other side it would come to rest at a distance of mg by k minus mg by 4k. mg by 4k is the amount by which the extension will reduce. So this will be 3 mg by 4k. It will again travel that same amount. Then on the left hand side the compression would be 3 mg by 4k minus mg by 4k, mg by 2k, and so on. But when will it actually stop permanently? So for permanent rest, we must have the spring force lesser than or just equal to the maximum possible friction when the block comes to rest. At that instant, if the spring force is not able to overcome the maximum friction, then the block will be permanently at rest. Mg by 8k by substituting mu. So we just have to figure out when the maximum compression extension will be lesser than mg by 8k. So here again it will travel back for mg by 2k. Then on the other side it will travel mg by 2k minus mg by 4k. So it will be mg by 4k. And now this mg by 4k will again reduce by mg by 4k. That means the final compression or extension will be 0. So it will come back to the natural length, and at natural length the velocity will be 0, and of course at natural length the spring force is 0, so it is not able to overcome the maximum friction, and thus the particle will come to permanent rest at the natural length. In this particular question it's happening, it's a coincidence that it's coming to rest at the natural length permanently, but that will depend on the coefficient of friction value in general. So let's calculate the total distance traveled. The total distance traveled would be mg by k plus twice of 3 mg by 4k plus mg by 2k twice plus twice of mg by 4k, and so that will come out to be 4 mg by k. I've included a question based on this concept in the DPP homework, so you'll get to practice there this kind of a problem. Now let's come to vertical circular motion. So broadly, vertical circular motion is categorized in as two categories. One is constrained motion, where the particle is forced to move in a circular path, and the other is unconstrained, where the particle may go out of the circular path and may perform free fall motion. So the example of constrained circular motion is I have a rod to which a particle is attached. So the particle is forced to move in a circular path. On the other hand, an unconstrained example would be a string. A string can become slack. So at some point it is a possibility that the string becomes slack, tension becomes 0, and the particle performs projectile motion. The other examples are you have a ring on which there is a bead. You have a fixed ring, vertical ring on which you have a bead. So the bead is of course forced to move in a circular path. Or you have a circular pipe in which a particle may travel, once again forced to move in a circular path. The other example of unconstrained motion would be inside a vertical circular track. A particle is traveling and it may lose contact at some point and perform projectile motion. So those are the kinds of unconstrained circular motions. In the case of constrained circular motion, the minimum speed, when the particle is at its bottom position, the minimum speed to complete the circle is given as root 4 gr. And the condition for this is at the highest position the velocity should be 0. So it should just reach the highest position with velocity that is just above 0. On paper we will write it as 0. And if the particle has even the smallest possible velocity at the highest point, it will come back down on its own and perform the entire circular motion. On the other hand, unconstrained, the minimum speed to perform the full circle, we should ensure that the particle does not lose contact at the highest point, or the string does not become slack in this case at the highest point, and that leads us to the fact that the minimum speed is root 5 gr. So this is the minimum speed such that the particle does not go out of the circular motion and completes the full circle. Let's also look at the variation of the force on the particle, whether it's by a rod or it's by a string or it's by the pipe. Let's just take a look at that. So let me just take the case where you have a rod. So let's say this is a light rod. Light rod means that it can only apply a force along its length. The reason is related to the concept of rotation that we will talk about later in the rotational mechanics chapter. So for now, just remember that a light rod can only apply a pulling or a pushing force. It cannot apply a force perpendicular to itself. So if I give it some velocity, it performs circular motion. Now initially, the force by the rod is towards the center because it has to provide the centripetal force. Gravity has a component that is radially away. So therefore, the force by the rod has to not only overcome the gravity component but also provide the centripetal acceleration. So the force by the rod given by these red arrows will be towards the center. So there is a possibility that at some point the force will become 0, and then the force is now outwards. So after this point the force starts acting outwards. Now this is the case in a constrained circular motion. In a constrained circular motion, the particle can experience this sort of an outward radial force by the rod or by the pipe. But in the case of, suppose you have a string, in the case of unconstrained, the motion will be exactly the same as the constrained motion until the point the force becomes 0. The force by the rod, once it becomes 0, it can change its direction. Rod can push as well as pull. However, in the case of a string, after the point the force becomes 0, the force here meaning tension. After the point where the tension becomes 0, the string cannot push like the rod. So therefore, after this point the string becomes slack and the particle is going to perform projectile motion. So that is where the difference begins between constrained and unconstrained. So in order to figure out where the force becomes 0, it's very straightforward. Suppose this angle is theta. I have mg. And the force here is 0, let's say the speed is v. So one equation that I can write is mg cos theta will provide the centripetal acceleration, so mv squared by r. And suppose you know the initial speed, can you get the final speed just by energy conservation or work energy theorem? If I just write work energy theorem, work done by gravity, since the particle is going up, the work done by gravity will be negative. So the height ascended is r into 1 plus cos theta. Should be equal to change in kinetic energy, half mv squared minus half mu squared. So if you substitute v squared here, you can solve for cos theta. So cos theta will give you the value at which the force becomes 0. So this is all in the case where the initial velocity is less than root 5 gr. When the initial velocity is just equal to root 5 gr, the force will become 0, force by the string or the rod will become 0 at the highest position. That is the condition basically for the unconstrained motion, where the particle can perform the full circular path. If u is greater than root 5 gr, if the initial speed is greater than root 5 gr, then of course the force will never be 0. The force will always be a pulling force. That means the force will always be towards the center. The force by the rod or force by the string or force by the pipe. This situation in the case of a pipe is slightly interesting because they can make a sort of a match the following question on this. That initially the ball is in contact with the outer wall, because the outer wall will apply a normal force that provides the centripetal acceleration. and at some point, as the particle is traveling, it is in contact with the outer wall. At some point, it will lose contact, which is basically the point where the force was 0. And then it will come in contact with the inner wall. So here we assume that the width of the ball is slightly smaller than the width of the pipe. So it's in contact with only either of the two walls, either inner wall of the pipe or the outer wall. And now once it comes in contact with the inner wall, then it's like the situation here, where the force is radially outwards. The normal force will now be given by the inner wall. So they can ask you in the match the following question that given they'll give you some initial speed, then they'll ask you at some angle, is it in contact with the inner wall or the outer wall? So you just have to check whether the force is becoming 0 and at what angle. So beyond that, the particle will be in contact with the inner wall, and before that the particle is in contact with the outer wall. Now let's do a question. So this is a hemispherical bowl. The inner surface is a hemisphere, and a particle of mass small m is released from rest. Let's say the wedge has a mass capital M and the coefficient of friction is 1. The wedge inner surface is smooth. The coefficient of friction is 1 between the floor and the wedge. The question is asking us, find the maximum possible value of the particle mass of small m such that the wedge does not slip. Alright, so give it a try, then you can take a look at my solution. Okay, so let's first figure out what will be the velocity of the particle when it travels, let's say, an angle theta. So let's say this angle traveled is theta. Can I write energy conservation or work energy theorem? So the height descended is r sine theta. So the work done by gravity would be mg r sine theta. The initial velocity is 0, final velocity, let's say v. So the work done by gravity should be changed in kinetic energy. And therefore v will come out to be root 2 gr sine theta. And if I were to calculate the normal force on the particle by the wedge, I have gravity as well acting, and this angle is theta. So towards the center, can I write n minus mg sine theta, component of gravity along the normal, should be equal to the centripetal force mv squared by r. So my normal force will come out to be, just substituting v here, 3 mg sine theta. So this is my normal force by the wedge on the particle, and that will also be the normal force by the particle on the wedge. So now if I draw the FBD of the wedge, I'll have a normal force this way, capital Mg for the wedge, a ground normal, and I'll have a friction, a static friction to the right, which will balance out the horizontal component of this normal force. So first let me write down the vertical force balancing n dash should be equal to capital Mg plus the vertical component of the normal force. It will be n sine theta, so I may just substitute n. So that will be 3 mg sine squared theta. And the horizontal component of the normal force, which is trying to accelerate the wedge, should be lesser than or just equal to the maximum possible value of the frictional force. So can I write n cos theta should be less than equal to mu n dash. And so n is 3 mg sine theta, so 3 mg sine theta cos theta should be less than equal to mu n dash, and mu, the value of mu is 1 and the value of n dash is this expression. Alright, now I have an inequality for m, for small m. So now it's just a bit of mathematics. So can I write m should be less than equal to sine theta cos theta minus sine squared theta. Let me just write this as just converting it into 2 theta, it will be a little easier. Let me write sin square theta as 1 minus cos 2 theta, so this will become plus cos 2 theta minus 1. Alright, so now I have an inequality for small m. So for this wedge to not slip, the value of small m must be lesser than equal to this value for all angles. That is the key point. The mass small m should be lesser than this RHS for all angles. So if small m is lesser than the smallest value of RHS, then it will be lesser than every other value of RHS. So let us figure out what is the smallest value of RHS. So for that I need the largest value of this denominator, sin 2 theta plus cos 2 theta, and I know that from trigonometry, or you can even use calculus, that largest value would simply be root 2, and therefore m should be lesser than the smallest value of RHS, and the smallest value of RHS would be root 2 minus 1. So m should be lesser than equal to this is the largest value of small m that you can have such that the wedge does not slip. A frictionless circle of radius r is made out of a strip of metal and held fixed in a vertical plane. So this is the circle. A massless spring with spring constant k is one end attached to the bottom of bottom point on the inside surface of the circle. So here, and the other end is attached to the mass m. The spring is compressed to 0 length. So initially it is at 0 length with the mass touching the inside surface of the circle at the bottom. So the mass will be at the bottom. Whatever negligible length of the spring remains, it's is essentially horizontal. So that means when the particle is released, it will get a small push to the right and then start performing circular motion. So the spring is then released and the mass gets pushed initially to the right and then up along the circle. The setup at a random later time is shown. So this is at some general instant. And let L be the equilibrium length of the spring. What is the minimum value of L for which the mass remains in contact with the circle at all times? That means the normal force has to be non-zero at all times. If you look at the highest point, that is when the particle has the likeliest chance of losing contact, because at that point the spring will have maximum extension at that point and will be pulling it downwards to the maximum possible force. So we are going to set the normal force at the highest point to just 0. Let's take a look. So let's say length L is the equilibrium length as given to us. So at this point the extension would be 2r minus L, and let's say the speed there is v. So can I just write down the force equation that I have mg and I have the spring force. Normal force is just 0 at that point, so I'll have mg plus kx, so k into 2r minus L should be equal to mv squared by r. So this is one equation, and the other equation is that the initial speed is 0, so I can do energy conservation. So if I take the lowest point as the reference line for 0 gravitational energy, so 0 potential energy for gravity. So what is the initial spring energy? The spring is compressed by an amount of L. L is the natural length and initially its length is 0. So initial spring energy is half k L squared, gravity is 0, kinetic energy is 0, and finally the spring energy would be half k into extension is 2r minus L the whole squared. Gravitational potential energy would be mg into 2r, the height is 2r, plus half mv squared, final kinetic energy. So this is basically energy conservation. So what I'm going to do is I'm going to substitute mv squared here and I'm going to solve for L. Half k L squared is half k 2r minus L the whole squared plus 2 mgr plus, so I'm going to substitute the value of mv squared, which will be mgr plus r times k into 2r minus L. Now all you need to do is solve for L. So I'll leave this calculation up to you. It's very straightforward, just basic algebra. In order to get the value of L, mg by k plus 6r by 5. Now that's a very cute shortcut in vertical circular motion. if a particle is given some velocity which is less than root 5 gr and it's connected to a string, and it performs circular motion, and at some point tension becomes 0. Let's say that angle is theta. So the motion of the particle is going to be projectile motion, but at some point the particle is once again going to be at a distance r from the point of suspension. So the string will become taut again, and let's say that angle is alpha. So there's a very nice relation, alpha is equal to pi minus 3 theta. So the string becomes taut again at this value of alpha, which is equal to pi minus 3 theta. So this is a very useful relation. I'll show you a type of question where you can use this shortcut method. One thing to note here is that if alpha is negative, that means the projectile was in this manner and the string became taut on the right hand side of the lower vertical. We measured alpha to the left of the lower vertical. So this will be alpha. So alpha, I'll say it's mod alpha. So if alpha is negative, that means the situation is this way. The string is becoming taut when it's on the right hand side of the lower vertical, or rather on the same side as when the string became slack. Let's take a look at a question where our shortcut is applicable. So I have a particle attached to a string. It's given some velocity u. It's less than root 5 gr, the initial velocity, therefore it will lose, or tension will become 0 at some point, and then it will perform projectile motion. The question says that during its projectile motion, the particle goes through or reaches its initial position, the bottom position. So the question is asking us find the initial speed. So here the string will become taut again when it's back to its initial position. That you should realize, because the particle will be at a distance of r, the string length is r, from the point of suspension when it returns back to its original position. So therefore, you should be able to see that the value of alpha is 0, and therefore theta would be pi by 3. Remember, alpha was pi minus 3 theta. Okay, so the string is becoming slack when it's at an angle of 60 degrees to the vertical, and therefore can I get the speed there? Now it's very straightforward. I can just write mg cos 60, so mg by 2 is mv squared by r. So I get the speed as gr by 2, square root of that. And now it's just either work energy theorem or energy conservation. So the particle is going up at a height of 3r by 2 from the bottom. So work done by gravity would be minus mg into 3r by 2, should be equal to change in kinetic energy. So just substitute v squared here, and you can solve for u, which will come out to be root 7 gr by 2. So that's your answer. So we didn't have to use the equation of trajectory, which is the standard way to do this question. Just use the shortcut formula and you can get it very easily. Now let's talk about how we can use work energy theorem in a non-inertial frame. In a non-inertial frame, when we write work energy theorem, we need to include the work done by the net force, so that includes the pseudo force. So work done by the real forces plus work done by the pseudo forces should be equal to change in kinetic energy. And this kinetic energy will be relative to the non-inertial frame. So for example, let's say I have a hemisphere or semicircular disc. I have a particle resting on it, everything is smooth. And this semicircular disc is now being accelerated horizontally with a constant acceleration a0. So the question is asking us to find the position where the block loses contact. So initially the block and the hemisphere have 0 velocity. So it will be easier to go in the frame of the hemisphere, because in the frame of the hemisphere, the block will be performing circular motion. So the block will perform circular motion, and let's say at this theta, at this angle, the block loses contact, means normal force is 0. So when the question is asking us to find the position, we can just find the angle at which the block loses contact. So the forces acting on it are a pseudo force and gravity. Let's say the speed is v here. So what will be the equation that I can write? Towards the center, can I say the force of gravity is mg cos theta, and the component of ma naught pseudo force would be away from the center, so ma naught minus ma naught sin theta should be equal to mv squared by r. So this is just the force equation towards the center. And how will I get speed v? I can just write work energy theorem. So work done by gravity, the height ascended would be r into 1 minus cos theta. So work done by gravity would be mg into r into 1 minus cos theta. Now we have to also include the work done by the pseudo force. So the pseudo force is constantly in the horizontal direction to the left. So what is the displacement in the horizontal direction of the block? This green arrow, that is nothing but r sin theta. So can I say work done by pseudo force would be ma naught times r sin theta? And this should be equal to change in kinetic energy. Initially it was at rest, and finally it is equal to half mv squared. Now here you have to understand that v are both relative to the frame, so relative to the hemisphere. We've written the work energy theorem and the force equation both in the frame of reference of the hemisphere. And then you can just solve for these two equations. Hopefully they'll give you some good values for the acceleration. And so this is just basic equation in order to solve for theta. So just divide these two equations, so v squared will get eliminated and you can solve for theta. Now let's look at a general force where you've been given the force vector as some fx I cap, fy j cap plus fz k cap, and they are functions of the xyz coordinates. So the condition for the force to be conservative is del fx by del y should be equal to del fy by del x. Now what is this? This is a partial derivative. That means you're differentiating fx, the x component of the force, with respect to y, but you're treating x and z as constant, and you're differentiating with respect to y. Similarly, on the right hand side, you're differentiating with respect to x, but you're treating the y and z coordinates as constant. So along with this, we also require the other pairs. Del fy by del z should be equal to del fz by del y, and del fx by del z should be equal to del fz by del x. So this set of three equations must be satisfied in order for the force to be called conservative. So if I give you an example, suppose the force is 2x squared y I cap plus 2x cubed by 3 j cap. Suppose I want to check whether this force is conservative. So there is no z component here, so we only need to check the first equation. So what is del fx by del y? So the x component is 2x square y. Now I have to differentiate it with respect to y while treating x as constant. So 2x square will come out and I'll differentiate y with respect to y, which is nothing but 1. So the derivative will be 2x squared. Now I need to check del fy by del x. So fy is 2x cubed by 3, and with respect to x, can you see this will be 2x squared? Since both are equal, therefore this force is conservative. That's how you check whether the force is conservative or not. A common example of a conservative force is a central force. So a central force is something that is always directed towards or away from a fixed point, and the magnitude of the force depends only on the distance from the fixed point. It doesn't depend on the angular position. So the most common example of a central force is gravitational force or electrostatic Coulomb force. So central forces are conservative. That is the main advantage of a central force. where you can define a potential energy and the work done by the central force is independent of the path taken. So for example, suppose I have force as some k into, let's say, xi cap plus yj cap divided by x square plus y square raised to, let's say, 5. So what kind of a force is this? If you notice, this force is only in the xy plane. So can you see that r vector is xi cap plus yj cap, the position vector from the origin, and therefore the force can be reduced to kr vector in the numerator, and in the denominator x square plus y square is nothing but r squared. That will be r raised to 10. Now clearly this is a central force because it has only dependence on r, only on the distance, and it is directed away from the origin. It is parallel to r vector. So this is a central force, and therefore this is conservative. So whenever you are asked to check if a force is conservative or not, just first check whether it's a central force, because then that will save you a lot of calculation. You don't actually have to perform partial derivatives here anymore. So let's take a look at a question that can be asked. I have a particle here and it experiences a force, let's say F naught, which is always directed to this point, 90 degrees. Let's say radius is r. So the particle is constrained to move in the circle. So as the particle travels, the direction of the force keeps on changing, but it's always directed towards this point, let's say point P. The question is asking, find the work done by the force when the particle completes the quarter circle. The particle is performing circular motion, it's completing a quarter circle, and in that motion the work done by this F naught force is being asked. The magnitude of F naught is a constant given to us. So if you want, you can pause the video and give it a try. Think in terms of the central force, and you should be able to avoid any integration. Alright, so the standard way is to perform integration, and you have a force acting this way, and the displacement is this way. This angle is a variable, and you write work done as integral F naught ds cos theta, and you integrate it. But the easier way to recognize is that the force F naught is a central force, its magnitude is a constant, and it's always directed towards point P. So it has no angular dependence, and it's always directed to a fixed point. Therefore, it's a central force. So the path that the particle takes does not matter as far as the work done is concerned. And therefore, instead of the circular path, why do I not take the straight path? So let's assume that the particle is traveling along the straight path. So the force and the displacement now are parallel to each other. So can I just write work done directly as F into S, and S is nothing but R root 2. F is F naught, and that's your answer. So I hope you understood how the concept of central force helped us solve this problem in a very easy manner. Another example of a central force is the centrifugal force. The centrifugal force is given by m omega square r, where r is the distance from the axis of rotation. So for example, if I have a rotating frame, in that rotating frame, a particle is moving, let's say from point A to point B. Let's say this is RA and this is RB. So I want to calculate the work done by the centrifugal force from A to B. Now, because the centrifugal force is a central force, why is it a central force? Because it's always directed radially away from the center, and it is only dependence on R. There's no angular dependence. So it is a central force, therefore it is conservative. So if I want to calculate the work done by the centrifugal force, I can choose whatever path I want. I can even define a potential energy for the centrifugal force. Let me go ahead and do that. Can I write du is negative of the work done, change in potential energy is negative of the work done. So the potential energy would be Negative of the work done would simply be m omega square r dr. So that will be m omega square r square by 2 plus some constant. Let me say that the constant is 0. That's my choice. Basically at r equal to 0, I'm selecting the potential energy to be 0. So once I've defined the potential energy for the centrifugal force, work done becomes very easy. This is nothing but the negative of the change in potential energy. So negative of final potential energy minus initial potential energy. So initial minus final. So initial potential energy is minus m omega square by 2 r a squared. And what is the final potential energy? Minus m omega square r b squared by 2. That is the final potential energy at point B. So very straightforward equation. Let's do a question. A plane spiral made of stiff smooth wires rotated with a constant angular velocity omega in a horizontal plane about a fixed vertical axis O. So this is the top view and this is a spiral track. A small sleeve M slides along the spiral without friction. So this is a sleeve. Find sleeve means like a bead. Find its velocity v dash relative to the spiral. So v dash is relative to the spiral as a function of the distance rho from the rotation axis O, if the initial velocity of the sleeve is equal to v dot dash. So initially the sleeve was at point O, and then as the spiral rotates, it will experience a centrifugal force and it will keep traveling along the spiral. So if you want, you can give it a try. Think in terms of energy conservation, where you include the potential energy of the centrifugal force. Then you can take a look at my solution. Alright, so what I'm going to do is, I'm going to say that initially, when the sleeve is at point O at the origin, it's given a velocity of v naught dash, and finally the speed is v dash. So can I conserve energy? And the energy here includes the potential energy of the corresponding to the centrifugal force. So I can write half m v naught dash square. This is the initial energy. Initially r is 0. Centrifugal force potential energy was minus m omega square r square by 2 as we derived on the previous page. So finally kinetic energy has half m v dash squared, and the potential energy would be minus m omega square r square. So r here is rho. They've given a distance rho from the axis, rho squared by 2. So that's it. You will get v dash squared, or rather v dash, as v naught squared plus rho squared omega squared. Very straightforward if you understand the potential energy concept corresponding to the centrifugal force. Now let's look at how to calculate the work done by a variable force. So in general, I can say that my displacement is dx I cap plus dy j cap plus dz k cap. Infinitesimal displacement can be written in this manner. So when I have my force as fx I cap plus fy j cap plus fz k cap, I can calculate my force as integral f dot ds. That will be integral of fx dx plus fy dy plus fz dz. So this is a general situation. Let's look at an example on this. So let's say the force is given by 2x squared y I cap plus 2x cube j cap. And the question is saying find the work done from, let's say, 0, 0 to 2, 1. Now here they may or may not specify the path taken. If the force is conservative, then they won't specify the path, because then you can choose any path that you want. So let me just say this is 2 by 3. So that will make this force conservative, because it's the same example that I showed you earlier. Here, this is the same example that I showed you earlier. We showed that this is a conservative force. So let me just take that same force and let me calculate its work done. So because I can take any path, what will be convenient is to take a straight line path. So let me just go straight from the origin to 2, 1. So the path taken would be y is equal to 2x, and therefore the work done would be fx dx, so 2x square y dx plus fy dy. So 2 by 3x cube dy. The path here would be x by 2. Sorry. So one way in order to calculate this integral is replace this y by x by 2 and replace x here by 2y. Or you can even replace dy in terms of dx, whatever you're comfortable with. So what I'll do is I'll replace y here by x by 2 plus I'll replace x by 2y. And the limits for x is from 0 to 2, limit for y is from 0 to 1. Now it's a very simple integration. You can calculate the work done on your own. It comes out to be 16 by 3. If it's in SI units, then it will be in joules. So I hope you understood how to calculate the work done. If the force is not conservative, then they will specify the path. The path is basically used to convert this y into x and x into y in your integration. Now let's look at work done by friction. So let me consider the case of two blocks. So let's say the upper block has a displacement S1, the lower block has a displacement S2. Let's say S1 is greater than S2 and the upper block will experience a friction to the left, which will oppose the relative motion between the two blocks. So let's say that friction is kinetic friction. Alright, I want to calculate the work done by this kinetic friction, the net work done. So can I say on the upper block it will be minus Fk times S1 and on the lower block it will be plus Fk times S2. This will be the total work done by the kinetic friction. S1 minus S2. So this is the work done by the kinetic friction. First thing that you can see it is negative. And the other thing that you can see, it is independent of the frame of reference. This is displacement of 1 relative to 2. Whatever frame of reference you choose, this value is independent of that. So this is something that we will remember. Work done by the kinetic friction is independent of frame of reference. And therefore you can just calculate it in the frame of one of the blocks. So in the frame of block 2, just calculate the work done on block 1. On the other hand, static friction, can you see that in the case of static friction, S1 and S2 will both be equal and therefore the net work done by the static friction will be 0. So static friction does 0 work and therefore if friction is static, then you can conserve mechanical energy because the work done by the static friction is 0. However, kinetic friction is non-conservative and therefore kinetic friction, the work done by kinetic friction usually gets converted to heat. And that also makes sense that the heat produced should be independent of the frame of reference, and that makes sense with the fact that the work done by friction is also frame independent. Now let's talk about stability. So we are talking about the equilibrium position. So equilibrium means that the force is 0. And if I talk about one-dimensional case, see in general I can write my force, the x component of force as minus del u by del x, where u is the potential energy, Fy is minus del u by del y, and similarly for Fz. So in the case of one dimension, I can just write F is minus del u by del x. Here I'm assuming the motion is along the x-axis. So that means the equilibrium position means that del u by del x is 0, or rather let me just write it as du by dx. There's no need to write partial derivative, there is only one coordinate x. So the equilibrium position represents a minima, maxima or an extremum point of the potential energy graph. For stable equilibrium, df by dx should be less than 0. If you displace the particle by dx to the right, you should experience a force of df to the left so that the particle is able to come back to its equilibrium position. That is the whole concept of stable equilibrium. And this also implies that d2u by dx square would be positive because f is minus du by dx. So this is basically the minima of potential energy. Similarly, unstable equilibrium would be the maximum of potential energy, and neutral equilibrium is a point of inflection where basically d2u by dx squared is 0 as well as the slope is 0. So suppose you have a graph of potential energy versus x, something of this sort. So this will be a stable equilibrium position, this point will be unstable, and here where the slope is 0 and the double derivative is also 0, that will be a neutral equilibrium. Let's do a question now. So I have a potential energy function along the positive x-axis given by, so this potential energy function is given minus ax plus b by x for x greater than 0, where a and b are constants, and it's known that the system has only one stable configuration, stable equilibrium configuration. So choose the possible values of a and b out of the 4 possibilities. So if you want, you can pause the video and give it a try, then you can take a look at my solution and see if you've gotten it correct. Okay, so the question says that there is one stable equilibrium configuration. So stable equilibrium means the minimum of potential energy, so the derivative has to be 0. So since the potential energy is given by minus ax plus b by x, the derivative would be minus a minus b by x squared, should be 0. So I'll get the value of x squared as minus b by a. Now because we need real values of x, b and a should have opposite signs, only then x squared would be positive. So we'll keep that in mind, and knowing that fact that b and a should have opposite signs, immediately we can eliminate option A and option D. Alright. For minima, the double derivative should be positive. So double derivative of this would be 2b by x cubed, should be positive. So that means b should be positive. X is anyway given to be positive. So b should be positive and therefore a should be negative. So the option that will match our final conclusion is option C. So that will be the correct answer. And finally, let's come to power. Power is the rate of work done. I can write it as F dot V. This is instantaneous power, where V is the velocity of the point of application of force. Average power would be the total work done by total time. One kind of a question that appears sometimes is they give you power versus position graph. So whatever graph they give you, the area under the curve, what will that be? That will be power into dx. Now can I write power as, so we are talking about one dimensional case, so let me write it as the force into velocity into dx. So this is the net power, so net force, and net force I can write it as mass into acceleration, and acceleration I can write it as v dv by dx. And therefore I get this as mv squared dv. So from initial velocity to final velocity, I'll get the area under the curve as v cube minus u cube by 3. So they can give you the speed here at x1 and they can ask you the speed at x2, and you can just use the area and equate it to this to get the value of v, given that u is given. Alright, let's do a question now. A train of mass m traveling with a constant power p has a velocity v0 at t equals 0. The air resistance is proportional to its speed and is given by kv, where v is the speed of the train at any instant. Find the time taken for the train to double its speed. Alright, so the force that is producing this power P, that force on the train would be P by V, because power is given by force times velocity, and it's experiencing an air resistance of kV. So can I write P by V minus kV should be equal to m dV by dt. So P minus kV squared should be equal to m v dV by dt. And what do we need? We need the time, so dt would be equal to and now it's a case of integration, so I want to integrate from v0 to 2v0. So the right hand side integral should not be too difficult. You can make a substitution. So let me just write let p minus kv square be some z. So minus 2 kv dv would be dz, and therefore in my integral v dv I can write it as d minus dz by 2k. So let me just do it here. Let me take m outside and I'm going to substitute v dv as dz by minus 2k. So this will be my integral, and therefore my time taken would be minus m by 2k ln z, and I can substitute z as back again as p minus kv squared from v0 to 2v0. So now it's just basic substitution of limits. So what you'll get is m by 2k ln p minus kv0 squared divided by p minus 4 kv0 squared. So that'll be the time taken for the train to double the speed. So that's it for today. Do the DPP homework. Tomorrow the Pathfinder homework will be uploaded along with full video solutions. So do that. That's it for today. See you at the top. Good night.